Hello student, welcome to my channel The Learn Physics. Today I will be discussing the theory of work and energy. My discussions are, look at this: work, positive work, negative work, no work force, and example. Potential energy, kinetic energy, mechanical energy equal to potential energy plus kinetic energy is constant, that is conservation of mechanical energy, then power. Okay, I hope this video will be beneficial for you. Please like, share and comment the video. Okay, now let's start. Now first of all, definition of work. If a force acting on a body, look at this, if a force acting on a body and produces displacement S, then product of the force and displacement in the direction of force is called work done. So work done, W equal to force into S in the direction of force. Okay, look at this, if displacement occurs at an angle theta, so in this case work done becomes, look at this, W equal to F into S into cos theta. Okay, now the value of cos 0 degree, this is the 1, cos 180 degree, this is the -1, and cos 90 degree, this is the 0. Okay, now unit of work. In CS system, the unit of work is arc. 1 arc equal to 1 dyne into 1 centimeter. If a force of 1 dyne produces displacement of a body by 1 centimeter in the direction of force, then work done is 1 arc. Okay, if a force of 1 dyne produces a displacement of a body by 1 centimeter in the direction of applied force, then the work done is 1 arc. Therefore 1 arc equal to 1 dyne into 1 centimeter. Okay, in SI system the unit of work is joule. So look at this, 1 joule, this is the 1 newton into 1 meter. If a force of 1 newton displaces a body by 1 meter in the direction of applied force, then work done is 1 joule. Now we have to derive the relation between arc and joule. Look at this, 1 newton is equal to 10 to the power 5 dyne. Okay, and 1 meter, this is the 100 centimeter, so this is the 10 to the power 7 dyne centimeter. Now dyne centimeter means this is the arc. Therefore 1 joule is equal to 10 to the power 7 arc. Okay, understood? Now work done by the force. Look at this, if a force acting on a body produces displacement in the direction of applied force, then work done is positive work done or work done by the force. The accelerating force produces displacement in the direction of applied force, so work done by accelerating force is always positive. Okay, now look at this, if a force of 10 newton produces displacement 5 meter in the direction of applied force, then what is the work done? Now work done is equal to F into S. Look at this, this is the F and this is the S, so this is the 10 newton into 5 meter, so this is the 50 newton meter, that is, this is the 50 joule. So work done is positive and this work done is called work done by the force. Okay, now work done against the force or negative work done. At this, if a force acting on a body along this direction and body displaces this direction, okay, so the angle between them is 180 degree. In this case work done equal to F into -S, so this is the -Fs. Look at this, the force of friction always acting opposite to the direction of motion, so work done by force of friction is always negative. Okay, suppose a body moves along this direction, The force of friction acting on it is 200 Newton. If the displacement of the body is 5 meter, what is the work done? Look at this. Here force of friction is equal to 200 Newton and displacement is the 5 meter. So look at this. This is the minus 5. So work done. This is the 1000 joule, negative side. So this work done is negative work done or work done against the force. Okay, understood? Now look at this, a block. The force acting on a block, this is the mg. If the displacement of body along this direction, so the angle between displacement and force is 90 degree. So in this case, the work done W equal to, this is the F into S into cos 90 degree. Now cos 90 degree equal to 0. So in this case, F into S into 0. So this is the 0. So work done 0. So force acting in this case is called no work force. Look at this here, gravitational force F equal to mg acting on the body in vertically downward direction, but displacement occurs in horizontal direction. So work done in this case is 0. So if a student carry his school bag on his shoulder and moves on a horizontal path, the work done is 0. Okay, now look at this. The earth revolves around the sun in a circular path. Look at this here, gravitational force acting on the earth is directed towards the center and displacement along the tangent. So this angle is 90 degree. So work done by gravitational force due to revolution of earth is 0. Okay, understood? Next. So look at this. Here force and displacement is in the same direction. So it is the positive work done. Here force and displacement opposite direction, negative work done. Here displacement and force are at an angle 90 degree. Look at this. This is the 90 degree. So work done is 0. And force in this case is called no work force. Here this force no work force. Here this force is no work force. Okay. Next, potential energy. The energy possessed by body due to its position and shape is called potential energy. Now potential energy due to position. Suppose a body of mass m is on the earth's surface, is raised to a height h from it. So work done to raising the body, this is the F into S. F is the weight and S is the h. So this work done is the potential energy of the body. So potential energy of a body of mass m at a height h is mgh. Okay. Now potential energy does not depends on path follow. That is, if the body moves from this to this, and if the body moves from this to this and again this to this, then this. So work done in both the cases are same. Therefore potential energy does not depends on path followed. It depends on initial and final point. So it is a state function, not a path function. Not path function. Okay, understood? The potential energy of a body above the earth's surface or above a reference point is positive, and potential energy of a body below the earth's surface or below a reference point is negative. Okay, look at this. When a spring is compressed, it has ability to work done. So this compressed spring has a potential energy. The potential energy of the compressed spring is half k axis square, where k is the change of length and k is the force constant of the spring. Greater the force constant, greater the potential energy. Greater the change of size, greater the potential energy. Okay, understood? Now what is the potential energy of a body of mass 10 kg if it is brought to a height of 100 meter? Look at this. Here potential energy U, this is the mgh. Here m equal to 10 kg, g is the 10 meter per second square, and height Sn is the 100 meter. So this is the 100 meter. So look at this. This is the 10 to the power 4 joule is the potential energy of the body. Okay, and look at this. What happens if the body released from this height? Look at this, its potential energy decreases and kinetic energy increases. When the body reaches this point, the potential energy of the body becomes zero. When it just before touching the ground, then energy of the body is completely kinetic. Now kinetic energy. The energy possessed by body due to its motion is called kinetic energy. If a body of mass m moves with velocity v, then its kinetic energy k is equal to, this is the half mv square. Okay, so greater the mass of the body, greater the kinetic energy. Greater the velocity of the body, greater the kinetic energy. If the mass double, kinetic energy also double. If the velocity double, kinetic energy becomes 4 times. If the velocity becomes 3 times, kinetic energy becomes, look at this, 3 square, that is 9. Kinetic energy becomes 9 times. Okay, understood? Now we derive the relation half mv square. Suppose this is a body of mass m, moves with velocity u. A force F acting on it produces displacement s, and final velocity of the body be v. So what is the relation between u, v and s? Look at this. This is the v square equal to u square plus 2as. Here v square minus u square. This is the 2as. So this is the v square minus u square divided by 2s is the acceleration of the body. Now work done by the force. Look at this. Work done by the force is the force into displacement. Now force from Newton's second law of motion, force equal to mass into acceleration. Look at this. Here mass into acceleration, and this is the s. Now this is the m. What is the a? A is the v square minus u square by 2s into s. S cancel out. So this is the half mv square minus half mu square is equal to kinetic energy. Therefore work done is equal to change of kinetic energy. Okay, this is known as work energy theorem. Look at this. If u equal to 0, then work done is equal to half mv square. This is known as kinetic energy. Look at this. A body of mass m equal to 2 kg moves with velocity v equal to 10 meter per second. What will be the kinetic energy? Look at this. Here kinetic energy k. This is the half, m is the 2 and v whole square. So look at this. This is the 2 to cancel out. So this is the 100 joule is the kinetic energy of the body. Okay. Now momentum. Now we have to establish the relation between kinetic energy and momentum. Look at this. If a body of mass m moves with velocity v, its momentum small p equal to mass into velocity. Now from this relation we can get v equal to, this is the p by m. Look at this. If v equal to p by m is put here, we can get, look at this, k is equal to half, this is the m and this is the p by m whole square. Okay, so look at this. This is the p square by 2m. Okay, understood? So relation between kinetic energy, look at this, the relation between kinetic energy and momentum. This is the k proportionate p square. That is k proportionate p square. That is, if momentum becomes double, then kinetic energy becomes 4 times. If the momentum becomes 3 times, then kinetic energy becomes 9 times. Understood? Now another relation between momentum and kinetic energy. Look at this. Here p square equal to 2mk. Therefore p equals to root under of 2mk is the another relation between momentum and kinetic energy. Now two questions. Look at this. Two bodies, one small m and another capital M. Small m less than 1 have same momentum. Momentum of this body p, momentum of this body p. Which have greater kinetic energy? Look at this. Here k is equal to, look at this, p square by 2m. and here K2 equal to P square by 2 capital M. Look at this. Here kinetic energy inversely proportional to mass when momentum is constant, as small m less than capital M, so K1 greater than K2. Okay. Now another question. Look at these two bodies. So a small body and a large body have same kinetic energy, which have greater momentum. Look at this. Look at this. When kinetic energy constant, the momentum is directly proportional to square root of mass. Here mass more, so P2 greater than P1, as M2 greater than M1. Understood? Okay. Now conservation of mechanical energy. Suppose a body of mass m is raised to a height h to the point A and it is rest. As body is at rest, so look at this. Here kinetic energy Ka, this is the half into m into 0 square, that is 0. What is the potential energy UA? Look at this. As height of the body at the point A is h, so its potential energy is mgh. So this is the mgh. Therefore mechanical energy me, this equals to kinetic energy plus potential energy. So this is the 0 plus mgh, this equal to mgh. Okay. Now the body is allowed to fall. When the body reaches at the point B, its displacement is x. If v is the velocity at the point B, so look at this. This is the v square equal to 0 square plus 2as. Here 0 square plus 2. Here a is the acceleration due to gravity and s is the x. So here v square equal to 2gx. Now what is the kinetic energy at B? Look at this. Kb, this is the half m v square. V is the 2gx. Sorry, but v square is the 2gx. So this is the half m into 2gx. So this is the mgx. Okay, understood? Now potential energy. Look at this. The potential energy UB. This is the now height of m at the point B is h minus x. So potential energy, this is the mg into h minus x. So this is the mgh minus mgx. Therefore mechanical energy at the point B, this is the kb plus ub. Look at this. This is the mgx plus mgh minus mgx. Okay. So this and this 0. Therefore this equal to mgh. So look at this. Here mechanical energy mgh, here mechanical energy also mgh. Therefore mechanical energy of a free falling body is conserved. Okay, understood? Now power. Power is the rate of doing work. That is power capital P. This is the work done by time. Now work done is the force into displacement. So power is equal to force into displacement by time. Look at this. P equal to S by T is the V. So force into velocity. Therefore power is equal to work done by time equal to F into S by T equal to force into velocity. Now unit of power. In SI system, the unit of power is watt. 1 watt is equal to 1 joule per second, and in CJ system it is arc per second. If a person or a machine performs work done 1 joule in 1 second, then its power becomes 1 watt. Okay. Now two person A and person B, both lifts 10 kg mass 10 meter, but A performs in 1 second, B performs in 2 seconds. Which have more power? Look at this. We know work done here W equal to mgh. M is the 10, G is the also 10, and H is the 10. So this is the 1000 joule. But look at this. A performs this work done in 1 second, but B performs in 2 seconds. So look at this, the power of A, this is the 1000 by 1 watt, and now power of B, PV equal to, this is the 100 by 2 watt, that is 500 watt. Okay, so A is more powerful than B. Okay, now commercial unit of energy. Look at this, we know P equal to work done by time, that is energy by time. So energy equal to power into time. Okay, the commercial unit of energy is kilowatt hour. Now 1 kilowatt hour means 1000 watt into 3600 second. Okay, so this is the joule. Therefore, this is the 3.6 into 10 to the power 6 joule. Therefore, commercial unit of energy is kilowatt hour, and 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joule. Okay, many thanks for watching this video. I hope you understand this video. Please like, share and comment on this. And don't forget to subscribe my channel to learn physics easily. Okay.